Working on the project. I guess that's probably true. It's due today. So I'd like to introduce our speaker for today, Junjie Hu, who will be talking to us about machine translation. Take it away, Junjie.
Yeah. So hello everybody. I'm going to cover the topic of machine translation and give an overview of both statistical.
Okay. Sorry.
Yep. So, hi. So I will give an overview of both statistical machine translation system and the current popular model on neural machine translation. So one might wonder that if the problem of translation actually can be treated as the problem in cytography. So, for example, you see a foreign sentence and you notice that this sentence is written in Russian or in some Chinese, and you notice that there is a corresponding English translation of that sentence, and you just want to decode the sentence, the articles in foreign language to the other language that you know. So, for example, here we have a website that is written in English, and there's another corresponding Chinese translation. And we want the machine translation system would translate the sentence in foreign language to the other language. And for example, the other example is Bible. We have the Bible in English and we have the Bible in Chinese, and we want to translate the text from one language to the others.
I think there's a problem I have to fix. I'm sorry. Yeah. Okay, it's fine. Sorry.
Yeah, so no problem. So, and the other example is that we have some books that are written in English, and there's a corresponding translation in Chinese. And also we have some manual. Look at the manual on the left. We know that there's a English translation and there's a Chinese words here. So by observing the similar patterns on the last character of all the Chinese translation, we know that they are pretty similar. And we can more or less guess what's the last character of this word. So can anyone guess what's the last character of these words? Yeah, that's correct. So you know that there is a clear correspondence between the Chinese translation and the English sentence. And you can clearly guess the first character of the second and third row is like chicken. Yeah, so by the statistical machine translation system, take advantage of calculates the frequency of words coexist in both the foreign language and the English sentence. And the other example, like we have some articles written in the STOM. We want to translate those articles, and we see what happens in the history. And so first I will introduce the noisy channel MT. So suppose that we have someone talking to you in a language that you don't know, and we treat this as the confusing foreign language. And conditional on this foreign language, we want to estimate the probability of translating those foreign language to the English sentence. So in traditional, we write foreign language by F and English by E. We want to translate a foreign language to English, and we call the foreign language as the source language and the English as target language. Sorry. And the noisy channel basically means that you have a language model. The language model P of V were trying to estimate the probability of a grammatically correct sentence E. For example, you have a sentence E, and that samples from the probability distribution of E, and then it goes through some noisy channel conditional on E. You can output a foreign language. Someone says a foreign language, and you receive the foreign language, and you want to decode the foreign language to recover the English sentence here. So it follows the intuitive way, like we want to find the translation of E given F can be decomposed to P of V times P of F given E divided by P of F using the Bayes rule. So in that case, we want to find the most likely translation in English by taking the Rmax of the conditional probability here. And we know that if you want to find the correct translation in E, E doesn't have any relation with P of F, so we can ignore the denominator here, and we just focus on the two terms here. So this is the language model that trying to estimate how well this translation output is, and this is the translation model. This language model trying to estimate the fluency of the translation, and the translation system were trying to estimate the adequacy of the translation system given this E. So why would we model this translation using the noisy channel here? Because one advantage is that we can use lots of monolingual data to train a good language model. There's a bunch of in-domain English sentence here. We can train a good language model, and it will estimate how well your translation is sampled from the domain you cared about. And the translation system, we can use a parallel sentence to trying to estimate the translation, the lexicon translation probability or the phrase-based translation probability. And we will cover it in the next few slides. So for the language model, it will estimate the fluency or grammatical check whether the sentence is grammatically correct or idiomatics. And we can use any language model like N-gram language model or neural language model. And for the translation system, it reverses the way that we want to translate. We want to estimate the probability of P of F given E, and it helps to ensure the adequacy of the translation. But so we sorry.
So does that mean that using this model,
Mm-hmm.
in order to translate from the foreign language to English,
Mhm.
you have to know how to translate from English to foreign language?
Not necessarily, but you can estimate the probability by word alignment. I will cover it in the next few slides. So basically, if you know because we eventually run the word alignment toolkits, and then we can estimate the probability in the lexicon level. So we can estimate either P of F given E or P of E given F. But the advantage here by using the language model here is that we can leverage large amount of monolingual data.
Okay.
Yeah. So here, for example, language model, if we don't have the translation model there, only using the language model, it will just keep saying some words, trying to generate some words, and it doesn't trying to find a correspondence between the source and the target sentence. So it were trying to, for example, keep talking about some nonsense sentence and not related to the source sentence you cares about. Yep. So this is why we want the translation model. The translation model, for example, here we have a foreign sentence in French, and there are three possible translation output here. Oops, I don't.
Just that.
Okay, that's fine. Yeah, and we know that one of the possible translation is like I would like some trees, and I would like a little of trees. These two translation outputs are more or less more likely than the third one. So the translation model will try to give a very low probability to this sentence. And so how can we parameterize the translation probability? The naive way is that we can estimate the translation probability by the frequency. So we count how many times this F and E coexist in the parallel sentence. Okay. And then we count how many times this English sentence appears in the training corpus, and we use these two numbers. We divide by the total number of English sentence, and we can estimate how well this translation probability is. But there's a lot of sentence. It wouldn't generalize to some new inputs. It only can estimate the lexicons that exist in the training data. But for a neural model that we will cover in the later part, we can see that using distributional embedding, it can help to generalize to some new outputs. So there's an example here. Horse is I think it's a word in German. House is a word in German, and there will be translated to house or home, shell, and we know that the lexicon translation might not be one-to-one. It would be one-to-many. So there's multiple translations. Some are very common. For example, house is translated to house or home most of the time. But shell, sometimes it can be a proper translation. For example, the house of snail is shell, something like that. And we also know that different word sense or different register, different infraction may affect the translation. We may choose different word level translation in the dictionary. And so this is what I have introduced here by counting the number of times that house, home, shell appears in the training corpus. And then we can divide it by the total number of all these words, and we can get the estimate the probability of P of E given horse and E equal to house. The probability, what's the probability of that? And actually using the frequency using the frequency to estimate the translation parameters here is the MLE solution. So MLE, we know that we're trying to maximize the data likelihood. So once, for example, we know what the data looks like, how many times those data coexist in the training corpus, we're trying to have their count, and this is the MLE solution.
So how does the training corpus look like? Because in the beginning we began with sentences,
Mm-hmm.
and now we are into words.
Yes. So the process is like this. We run a word alignment. We can find the word alignment. And then based on the word alignment, we know that some of the word coexist with a translation word, with its aligned word. And then we estimate the probability based on that. And I will cover the word alignment in the next few slides. This is just an overview about how we can estimate the translation probability here. And after we go through the word alignment, we can have a better estimation of this probability. And there's a lexicon translation. For example, we know that this English sentence and foreign sentence has multiple words, and we know that the words can have some alignment. So we have some assumptions that each English word is generated from exactly one word in F. So for example, each English word is aligned to each exactly one word in the foreign language. And then we have a latent alignment parameter AI that indicates which English words comes from which English word comes from. So it basically it align this word, for example, the English word EI to FAI here. And so here we have a latent alignment. So we only observe the source sentence and the target sentence, the English sentence and the foreign sentence. And we want to estimate how well those words align between, for example, EI up to EM, align to F1 up to FN. So, and we also have another assumption is that given the alignment, the translation decision are conditionally independent of each other, and it only depends on the aligned source word FAI. So that means when you hear the word FAI, you know that by the alignment you can find where it is originally from. So you can find the source word, and then given the source word, the translation decision are independent. So in that case, you can decompose the translation probability. Translation probability, for example, we previously when we want to estimate P of P given F, and we assume that we have M words in the English, and we want to estimate the alignment probability here, given the foreign language. Let's say you hear some foreign language in French, and you want to guess. You have a rough guess how many words, how many English words it would be. For example, M. It can be a predefined number, and we want to estimate the alignment probability here. And we also, let's say I have a specific word alignment A here. A is a matrix, is a vector, it's an n-dimensional vector. And if we given the A here, and we know that one of the foreign words actually comes from the English words here, and those translations are independent, we can decompose the conditional probability into word level, and then we marginalize all the latent variables here of A here, so we can get rid of A here, and we can have an estimation of P of E given F. Is it clear? So what we observe is only E and F, and we want to estimate the alignment between E and F. And alignment vector is actually a latent variable. We can marginalize the latent variable to get the translation probability, and then we come to a big problem to estimate the alignment probability. So most of the SMT paper in the first 10 years is trying to estimate the word alignment probability. So there's lots of toolkits like FastAlign or Giza++ or Giza. These toolkits are trying to estimate how well the translation alignment, the word alignment is. Is it clear? So a naive way is that we can, for example, suppose that we can assume that all the alignment align one word by one word in the same order. And then this sometimes works pretty well, but for some language that are quite different, their order might be different. So if you, for example, come across some German, this is German sentence, and the order sometimes are mixed. And so we know that the translation probability, if you know a dictionary, it's easy to estimate the translation probability, but sometimes the word order is more difficult. Yeah.
Isn't this a special sentence because it is just like a calculus? You can kind of switch around what comes first.
Oh yeah.
So you might say the house is smaller. You could say like small is the house. It's like kind of a weird sentence, but
Mm-hmm. Yeah, this is a toy example. So in the real case, actually the model can learn the word order. So this is I think this is a toy example that I just shuffle the order in the source side, in the foreign language side. But for some like very different language, like some will put the word in the end of the sentence, some will put the word between the subject and object, and you clearly have the reordering problem.
yeah, it's a weird thing with words.
Yeah. And some of the words, some of the source words might not be translated at all. So we probably, so for example, we would have a null token here. So for some of the words that are not translated, we will align this word to a null token here. And so, sorry. Okay. Yeah. And there's another sentence. For example, if a source word can be translated into more than one target word. For example, this word, I combine them together, translate to two words, and we have the alignment here. So, for example, this word, all the source words is aligned to the first foreign sentence, foreign tokens here. But if two source more than one source word are translated into one token, what happens? Can we write the alignment like this? No, it's so there will be a problem, but in that case, there's an extension of word level lexical level translation. It's a phrase-based MT system, and I will cover that in the few slides. So basically, what the intuition is that rather than treating each word, the sentence by word, we treat the sentence by phrases. And we segment, for example, this is one phrases, and this is another phrases with one word only. And this phrase is aligned to these phrases, which consists of two words. And just now we mentioned about the alignment model. IBM Model 1 is a very popular word alignment model. It's trying to trying to estimate the translation alignment based on some very heuristic rule. It assumes that the alignment distribution for each AI is actually uniform over all the source words and the noun tokens. So here, for example, you start from the very simple alignment vector. It is a uniform vector draw from. It's a vector draw from a uniform distribution. And here, for example, if you come across a sentence that are very simple, you find the word alignment like this, and you generate the translation output like this. The language model say this is a good translation. But what if the model have bad alignment, and it will just shuffle, it will have some weird order of the translation output like this. And the language model says that this is not good. And we clearly want to fix it. And so this is a chicken and egg problem. So if we have, for example, if we have a good alignment, we can have a better translation probability by MLE. But if we have the translation, if we have a good translation probability, we can find the most likely alignment. But we cannot both have a, we cannot assume that which comes first. So in that case, what's a good strategy to find the balance between that? Can anyone try that? So if we have a good translation probability, we can find a good alignment. If we have a good alignment, we can find a good translation probability. But we just don't know which one comes first. So can anyone try? Yes.
Bootstrapping.
Bootstrapping, yeah. But bootstrapping.
We first start with a little bit of
Mm-hmm.
and annotated data.
Mm-hmm.
And try to build it up from there.
Mm-hmm.
I don't know.
Yeah. Good guess.
I think maybe you start somewhere and then you start fixing like going in this loop.
Yeah.
At the end of
Yeah, exactly. So let's say we can first assume that the model, the alignment actually comes from a uniform distribution, and then we trying to estimate, gradually iteratively update the model, and we guess how the alignment vector converge. So here is an example. So we pick some random starting parameters like uniform distribution, and then we run through the following iterative process. We're trying to, given the current parameters, we compute the expected alignment probability P of AI given E and F. And we use this alignment probability. We can try to keep track of all the aligned words, and then we count the number of times F is used is aligned to the source word, and then we can update the parameters by frequency estimation. By MLE estimation, we maximize it using the MLE estimator, and then we iteratively go through this process. And after that, the alignment probability will have a good estimation. So let's go to see. So I think this is a very typical way to estimate the latent variable. For example, you only have the observed sentence in both languages. The latent, you don't have the alignment. The alignment vector is the alignment probability is latent variable. You want to estimate how well those tokens align to each other. And for example, this is the training data. We know that suppose we have a uniform alignment probability here. So each target word is uniformly aligned to all the source words plus the non-tokens. And based on the observation here, we know that lar is most likely aligned to dir in the first iteration. So in this case, we count how many times dir aligned to dir, and then we can update the probability of the translation probability of dir given lar, and then use that. And after another iteration, we know that this for example, floor might align to flowers here, and then we keep iterates the process, and after another iterations, and we know that the translation probability will converge to a very stable numbers here, and then we have the translation probability. This is what you asked just now. We can estimate the translation probability here, and we also have the word alignment here. So this is another example after running uh, a few iterations. Usually we use 5 iterations to run to have the model converge to a stable point. And then we can have a translation table. Here's one of it is the source, one of it is the English word, one of it is the foreign word, and then the translation probability. So, just now we also mentioned that if more than 2 words align to one source word, how can we deal with that? We can extend the lexicon-based MT to phrase-based MT. So we treat the tokens in the phrase level. So for example, just now we treat all the tokens in the word level, but we can group a few words into one phrase, and then we know that, for example, these 3 words is actually a translation of one source word here, one target word here. And then we can use the same technique to estimate the translation probability in the phrase level, P of E given F in P of F given E in the phrase level. And we can also have some heuristic rule to constrain the alignment matrix. So suppose that we can estimate the alignment, each source word aligned to each target word aligned to each source word, and we can, for example, introduce a diagonal constraint. We constrain that most likely the source word in the ice prediction were aligned to the ice prediction in the target words. And we also can use some synthetic rules like tree structure. For example, if you observe that a sentence can be decomposed in a constituency tree like this, and we observe that a noun phrase is usually followed by GE here, one of, and you can extract some rules like the noun followed by GE can be simplified as XGE can be translated to one of the X. And you can replace this X by any noun phrase. For example, if the place token, you can replace it by country, you can replace it by house. So one of the house will be, this is maybe house GE, and that's it. And use the syntactic structure rule. Actually, we can extend the phrase level by synchronous context-free grammar. And there is a popular toolkit called CDAC developed by Chris Dyer here. And it's used the synchronous context-free grammar like this. And up to now, we talked about most of the technique in statistical machine translation system. So it basically contains the language model and the translation model. The translation model will estimate the translation probability, for example, in word level or in phrase level. And in the last decades before 2014, most of the research efforts are focusing on how to estimate alignment. And now we want to know how well our MT system performs. So the main idea is that the closer a machine translation output is to a professional human translation, the better it is. So the most common way is that we can compare the n-gram overlap between the MT translation and the human reference. And there is a very popular matrix called BREW. And the basic idea is that we can compare, for example, we can count how many unigrams exist in how many unigrams of the translation candidate exists in the reference sentence. For example, the word in red means the word exists in the reference. We have 3 references, and we can count how many times those words hit in the reference sentence. And we know that the unigram precision is 7 divided by 18. 18 is the number of the words in the candidates. But there's a problem. For example, if you just output duplicate words, and the word is very simple. For example, the candidate is 7 der, and you know that there is a word der in the reference sentence. So if you count how many words there exists in the candidate is 7, and you divide it by number of words in the candidate sentence is also 7. We have a problem here. So the solution is that once, for example, one word is matched with one word in the reference, we don't count the other word in the same token. So that would be 1/7 instead of 7/7. What if the system just output a sentence that are very short, only contains one word? The denominator will be 1, and if you just luckily hit one word, and the n-gram precision will be 1/1, it's perfect. But we want to penalize the model towards predicting too short sentence, so we want to add a gravity penalty to the matrix. So this is how we calculate BRUTE score. So the BRUTE score is actually the geometric average of the n-gram precision times gravity penalty. This gravity penalty will penalize the model of predicting too short sentences. And the n-gram precision will calculate. Just now we calculate the unigram precision, and for n-gram precision it will do the similar stuff. This matrix range from 0 to 1, and usually in the paper we'll scale the parameters by 100, and we usually can find that the anti-system can have a score between 10 to 30, but human translator can have a score between 70 or even 80. Yeah, and but this matrix is really difficult to improve. Usually, one BRUTE score can be a conference paper, or some people try really hard to tune the model to improve just one BRUTE score. And so here is an overview about the history. Before 2014, SMT is dominant in most of the applications. But after 2014, the neural MT comes up, and there is a tension mechanism trying to simplify all the other stuff. Because for SMT, actually it involves a very complicated pipeline. You need to do word alignment first, you need to extract the phrase, and you need to score the phrase table, and then you need to train the parameter and then decode it. But for NeuroMT, it simplifies all the pipeline by just have an end-to-end neural network to take, for example, take the source sentence as input and then output a translation. And it can generalize to some new data that are not exist in the training corpus. The SMT doesn't have the capacity to generalize to the new words, new inputs. So what does the neural network, where does the neural network do translation? Here, for example, we can, I would trying to first introduce the calculation of a neural network. The neuron is calculated by the weighted sum of the input and adding the activation on top of the weighted sum here.
Is there any reason why 2014?
Oh, I think because we have computational resource like GPU.
Oh,
And
was it like GPU skill stuff that really,
Yeah. One is the GPU resource we have. One is the parallel sentence we have collected during the previous decade. So for deep learning to work, you need to have a very big parallel sentences, parallel corpus. But for SMT, if you use, for example, 6,000 or 6,000 parallel sentence, you can still train a very good translation system because the phrase table are extract and then it's saved in the memory. But the deep learning model actually trying to memorize all the translation in its parameters. It's trying to parameterize the translation probability rather than estimate it and save it in the phrase table. This is the main difference. Suppose, for example, in the training data, you have the word-to-word translation, and the SMT will save the translation pair in its translation table.
Yeah.
But and every time you come across the source word, it will find the translation based on.
Are you saying there's a lot more parameters to predict in the neural model?
I would say, because the neural model has a huge number of parameters,
Yeah.
it requires lots of data to help it to train the model. But for SMT, actually you save the translation probability in the phrase table, and once you save it, you can refer it, and then you can trying to recover. You're trying to translate the word by looking the phrase table. But if the training data, for example, one phrase just appear one time in the training data, neural network cannot learn it quite well because you don't have so many data to learn the parameter well on the the word level representation and the model parameters. So that is why I think 2014 is a change point. We have the resource and we have the data.
Okay.
And we can have multiple layer, for example, we can have multiple outputs. For example, given the access input, we can estimate the probability, probability of 3 passes like that. And then we take the softmax and we can normalize the probability between 0 and 1, and we can have a prediction based on that. And we can have multiple layers. For example, have another weight matrix here. We multiply y by v, and then take another activation. We can have multiple layers. For example, we multiply y by v, and then take the activation function g, and then we can get another latent variable z here. And we can stack multiple layers. And here, if, for example, the activation is a linear function, actually it's a matrix multiplication of the original inputs here. But usually, we want to have some non-linear activation function in between so that the model can capture some subtle changes in the data. And we can also have different structures. Just now we mentioned about feed-forward neural network. We can also model the inputs by recurrent neural network. So the basic idea is that the input, the representation of y3 is conditional on the representation in its previous representation, previous token. So natural language processing is actually natural language is actually is a sequence. Most likely we deal with sequential data, and the representation of one word is usually depends on the previous words. So we usually want to capture the context information of the previous words. So we can use bidirectional LSTM. So the basic idea is that we go through LSTM in the forward path and the backward path, and we're trying to capture different context information from both directions. And here, so how can we represent the input? And we know that there's a huge number of layers in most of the neural network models, and we don't know how many layers, how many neurons, whether we want to use a recurrent neural network, what kinds of non-linear activities we want to try, and we know that there's bunch of work. There's a bunch of work trying to find a good architecture for a neural machine translation system. So first, we in the between 2014 to 2016, most of the neural machine translation system used recurrent neural networks. And then after 2016, Facebook came up with a convolution-based MMT system. And then after 2015, Google has the transformer neural MT. So people in different companies trying to compete and trying to come up with some good neural architecture to capture the context information. So here is one overview of the word representation here. So we know that we want to represent the word by a vector. So a naive way is that we can represent each dimension. We represent the word by a n-dimensional vector, and n is equal to the number of words in the vocabulary. And we can, for example, this is a very sparse vector. All the dimensions are 0 except one index, 1 for one word. So suppose we have for 50,000 vocabulary, we have one vector of 50,000 dimensions, and one of it is 1, and the others are 0. So we can note that clearly this is a very inefficient way to represent a word. So later on, people found that actually you can represent a word by distributional representation. So each word can be compressed to, for example, 300 dimensional space, and then each word in the 300 dimensional space can have some nice properties like words in the similar meanings grouped to each other. And we can use those vectors to represent the word more efficiently. So for example, here, dog can be represented by, for example, 300 dimensional vectors instead of 50,000 vector, sparse vector. And we can use some more advanced model like n-gram, character n-gram model, trying to learn the representation for n-grams in the word, and then combine the n-gram representation together to form the word representation. So the popular way to do it is by using the convolution neural network with the window of 3 or 2, trying to capture the bigram or trigram character representation, and then combine the character representation together to find the word representation. The advantage of using n-gram character n-gram model is that you can find some morphological features. You can find some words that are morphologically similar, and uh, uh, the words that are morphological variant. Yeah. And most of the neural network actually use supervised model to train the network, and we need a lot of input and output pair. We call it parallel corpus or parallel sentences, and this is why neural network can be another popular NP model, because we have collected a lot of parallel sentences, and those parallel sentences can help the model to learn the parameter so well. So the model goes like training algorithm goes like this. We run through a a bunch of mini batch, and then given each mini batch of input and output pair, we try to predict the translation y here, and we have the gold standard y star, and we compute the loss between the prediction and the ground truth reference, and then we use the popular backpropagation algorithms to backprop the gradient through the model parameters, and then update the model parameters by popular optimizers like SGD or Adam or MSProp, something like that. And once the model parameter converts to a stable point, and we can have some mechanism called early stop to end the process. And I think you cover n-gram model, right? So a very naive way to neuralize the n-gram model is that we can represent each word. For example, a bigram model, a trigram model. We have the previous, I think this is a fourth gram model. Yeah. So we want to estimate the translation probability, the conditional probability of EI given is, for example, 3 previous words, and we want to have a model to capture the context, and we can represent each word by the word vector here, and then we can go through some layers. For example, here, suppose we have for n-gram character n-gram model, we can try to use a convolution layer here to extract the word representation for this word, and then we can use the weight matrix in between to have a fully connected layer, and we learn the learn the higher level representation for this input, and then we can yeah, that's fine. And then we can use another layer map to the latent layer, and then we extract the context representation, and then we have another nonlinearity trying to estimate the conditional probability for the next word. You can use the n-gram character model here. You can use the word representation here. Either is fine. You can regard this as a lookup table, and then, for example, you have one word, and you look up the table and find its word representation, and then pass through a straightforward neural network, and then you extract the context. After you extract the context from the previous 3 words, you're trying to have another final softmax layer to estimate the probability of generating the next word, and then you have a Rmax to find the index of the next word. So,
So for the 2 combinational networks, would the weights for each of those be tied so that like each combinational network is learning the same weight?
yes. So usually for character n-gram, we suppose we have, for example, 10 filters, and then 10 filters are shared among all the words, and then we extract 10 vectors for the word representation. And then And 2003, Banjo actually has a paper to use this N-gram neural language model, and it finds that if you use more layers and more parameters, and you have fair enough of data, you can actually have a very good language model that can have lower perplexity here. So for language modeling, we usually use perplexity to measure the performance. And this is the traditional N-gram model. The above part are the neural N-gram model. And we found that using more layers and more hidden dimensions, we can actually have lower perplexity. And nowadays, people trying to test the language model on Pantry Bank coppers, and the number can be reduced as low as about 40 perplexity, and they have very I think they have very complex model, like you have a self-attention transformer-based language model, you have a LSTM-based model, and they are pretty good in predicting the next word. The advantage of using neural language model is that rather than currently we just talk about N-gram neural language model, but if you use INN-based language model, it can capture the long-term dependency of the sentences. So we can turn this neural language model into a translation model. Actually, language model is a translation model is a conditional language model. You conditional on the source data you observe, and then you translate it to an English sentence. For a language model, you only observe the previous tokens, and then you predict the next few tokens. But for translation, for MT, you not only observe the previous generated tokens, you also observe the source token, and you want to condition on the source token and generate the translation. So one way is that we want to follow the idea of alignment in SMT. So here, so we know that for translation model, actually we not only conditional on the previous generated generated tokens, we also conditional on its aligned source tokens. So suppose that we know the word alignment, like that in statistical MT, we can conditional on these tokens and then predict the next one. However, and we know that for neural model, when we trying to have more parameters, actually we can have better performance. We can, in 2014, Delvin actually used a recurrent neural network model to do the translation. And it basically goes through the source sentence by a LSTM model, and then pass the last hidden state to the decoder. And decoder is also an LSTM model. It's trying to decode trying to predict the next token given the source information and the previous target tokens. This one trying to start work, but we also I will also simplify the notation. For example, this is the vector, and we're just trying to have a rectangle here. And recurrent neural network looks like this. You have each word as the input to the recurrent neural network, and then we're trying to have its latent representation. And for recurrent neural network based model, they use the last hidden state of the encoder, and then they use that as the context representation of the source sentence, and then pass it to the decoder. The decoder will trying to decode the sentence based on the context vector. So nowadays, most of the popular neural model uh, follows the encoder-decoder architecture. The encoder trying to compress all the source sentence into a compact vector. The decoder will decode the sentence based on that to another language. But clearly, there's a problem. For example, you want to generate, you want to compress all the information to. This is the popular INN-based encoder-decoder model. But clearly, you can observe that if you want to compress all the information to a fixed size vector, you will come across the problem of long sequences. If the source sentence is too long and you want to compress whatever sentence into a fixed size vector, the model cannot remember so many contexts. So to help the model to translate one word by looking at the relevant source tokens, we have the tension model. So the tension mechanism is basically trying to associate the tokens in the target site with the relevant word in the source site. So suppose that you want to translate a word, you don't need to look at so many contexts. You only need to focus on just the most relevant words in the source sentence, and then you translate it. So, for example, here, we know that these two words can be aligned to our, and when we translate ours, we only need to focus on these first two tokens. It's very similar to word alignment. So attention is trying to mimic the procedure of finding the word alignment between source and target sentence. But there's another paper trying to say that word alignment is not, so attention is not exactly the same as word alignment, but they are very similar. They are often have one offset between the word alignment and the attention matrix. So there is an interesting paper. If you want to know, you can search it. And we know that this word is aligned to large. When we're trying to translate large, we have attention over all the source words, and we find the most relevant one, and then we translate it. And it go forwards, and we can find most of the relevant words. So how can we calculate the attention weight? So just now I mentioned, when we're trying to compute, when we're trying to translate the target word here, we're trying to estimate the attention weight between this word and all the other source words. So the basic idea is that we want to estimate the similarity of relevance between this word and the other. So what we did is trying to, for example, we can use many matrix to estimate the similarity between this word and the other word. The naive way is that we calculate the cosine similarity. The other way is that we combine these two vectors together and then go through a feed-forward network. And the feed-forward network, we're trying to estimate a real scalar that measures the similarity between these two tokens. And we can take the softmax to normalize the attention weights between 0 and 1. And then we can have a weighted sum use this weight. And we can have a weighted sum over the source word hidden representation to get the context vector. And we know that this context vector is very informative to predict the next word, because it's you can treat it, for example, this word, suppose this word is most relevant to the target word, and we have for 0.9, for example, 0.9 attention weight over this word, and then we have a weighted sum over all the word representation here, and this one clearly comes up here, most likely, and then you use this representation to combine with the previous context representation and you predict the next token. And it goes through the process. Given the previous word token, you have the current hidden representation for the previous context, and then you compute the similarity between this token and the other source token, and you find the most relevant context vector, and combine this vector and this vector, you can predict the next token. This is exactly the formula that we discussed before. The translation is actually a conditional language model. It's trying to predict the next word conditional on the previous content and the source token. And it keeps through until we predict the end token and the process ends. And most recently, there's other popular model like Transformer. It simplifies the recurrent architectures. And for example, in the previous model, we used a recurrent neural network. It's trying to compute the representation one by one. It's really difficult to parallelize all the process. Transformer actually have the advantage of parallelizing all the computation by using the self-attention mechanism. So the encoder is trying to compute the representation by self-attention over the lower layer representation. So what it does is that, for example, when we want to compute, for example, we compute the representation, higher representation of I here, we have for self-attention over the other words, and then we have a weighted sum over the other words, and then we can compute the representation here. And the same process goes for the other words. So in that case, you don't need to compute the word representation one by one. You can parallelize it to parallelize the computation, and then this word makes the computation much faster. And then the decoder we're trying to have her attention over the source, the higher layer source encoder, and then have her self-attention over its previous generated word tokens, and then predict the next token. It also follows the encoder and decoder architecture. The difference is that they use self-attention rather than recurrent neural network to do the encoding and decoding. And for convolutional neural network, actually they trying to use convolution filters to compute the word representation, higher word representation, and then compress all the information in the source side to some higher level representation, and then trying to decode it either by a LSTM-based decoder or some CNN-based decoder. And this is what they did. They basically have the same encoder-decoder architecture, and this is the difference. Rather than recurrent, they use self-attention. And the decoder actually have multiple layers. They can have mass self-attention. So because you don't have all the words when you decode the sentence, you can only have retention over the previous word that you have already generated. So this is called mass attention, mass self-attention. And the advantage of transformer is that you can stack multiple layers on top. Usually we stack over 6 layers, but for recurrent neural network, usually 2 or 3 layers, 2 layers is enough to learn a very good neural MT model. But for transformer, you need to have more than 6 layers. But the advantage is that when you're trying to compute the translation probability, is actually very fast. It doesn't involve the recurrency. And when you backprop the gradient, actually it's very efficient. You backprop through all the neurons rather than from the from the right neuron up to the left one. And also, one stuff is that because the transformer doesn't have uh, the uh, the order from left to right, we usually concatenate the word representation by a prediction embedding. The prediction embedding trying to memorize prediction of this word. For example, this sentence, we have 20-dimensional prediction embeddings, and each embedding, for example, is a sparse vector. The the index where this word is marked x1, and the others are 0. And we concatenate the word representation with the predictional representation together, and then put through the neural network. And Google trying to Google also used a very huge transformer system, and they found that they can save the training course by large amount, and then they can have a very competitive score between the convolution neural MT system and the INN-based MT system. And this is most of the work in neural machine translation system. We have the encoder-decoder architecture. The difference is that we have the attention. After attention, neural MT start to work. Without attention, it's horrible. But using different architecture can help you to capture different information. And transformer is start to dominates the field, but LSTM-based model is still very powerful. And the future direction of NeuroMT is that we can incorporate the syntax information from SMT to the neural model. How can we handle the morphological rich language? Because we want to represent the word into a vector. If the language is morphological rich, there are lots of morphological variants, but we want to represent those words in a very similar word embeddings. And we want to have, for example, the other direction is that we want to optimize the corpus level quality. So right now we only focus on the sentence level. We want to focus on the corpus level translation quality. And we also want to have a multilingual model. For example, you want to translate from multiple source sentence to sentence in multiple source language to English. And we want to have single encoder that can encode all the information in multiple languages to one vector, one uniform, map all the language into one single space, and then decode based on that. This is the main idea of designing the interlingual or some cross-lingual representation. And we also have some results on adapt the transform the knowledge that learns from the very similar high resource language to the low resource language. Suppose, for example, you have two languages that are that belongs to the same language family. They share most of the words, and you only have limited amount of the parallel sentence you have cared about. It's not enough to train a very good language NeoMT system, but you can borrow a large amount of parallel sentencing of similar language family, the language, and then you train the neural model and adapt the model towards the language that you are curious about. Yeah, I think that's it. Yeah. Thanks. Any questions? I can take a few questions. Yeah. Good. Yeah. Yeah. Thanks.